In my last video I showed you how to use an enthalpy change of combustion to construct an enthalpy cycle to calculate the enthalpy change of formation of cyclohexane. And today I want to show you how to use the enthalpy change of formation that we can calculate to work out the enthalpy change of reaction of any reaction that we feel like investigating. And so if you haven't seen the previous video, please click on the link. So we're going to start with the contact process here, which is used in ultimately the manufacture of sulfuric acid. This is a reaction which takes place in equilibrium, so we'll never actually get this reaction to happen. We'll always have a mixture of the products and the reactants. So what we need to do now is we need to work this out theoretically if we're going to make any predictions about the enthalpy change, or if we need to know the enthalpy change for any practical reasons, like making the equilibrium shift. We need to do this theoretically. It's almost impossible to do practically. So what we're going to do is go, right, okay, well, we know that these form from the same elements, and that gives us our second route. Remember, Hess's law is that if you go by one route or a second route, the first route and the second route will have the same enthalpy change. So our elements are sulfur. We've got 2 sulfur atoms, which is a solid, and we've got 2, 4, 6, so we've got 3 oxygen molecules, which is gas. Okay, and we're going to use data which changes from the elements to the compounds, like that, and these are going to be the enthalpy changes of formation. So we have the enthalpy change of formation of sulfur trioxide here, and I'm multiplying that by 2 again, because we have 2 moles of sulfur trioxide on that side, so we need this value to be twice as much, because the definition of this value is for 1 mole. Okay, so we've got 2, so we need to multiply it by 2. On this side I'm going to put the enthalpy change of formation for oxygen and the enthalpy change for formation of sulfur dioxide. Again, we've got twice as much sulfur dioxide, so I've put 2 there. If you remember your definitions, and if you remember how it works, then the enthalpy change of formation of an element is actually 0. So I've put the term in here just for completion, but actually when we calculate that, it's 0. If I refer to my table, I find that SO2 is going to be 2 times 297 minus, and I look on the other side, I'm going to find it's going to be 2 times 441 minus. There it is. And so if I plug my numbers in here, I get that. If I plug them through a calculator, I get these values here. So let's find our 2 routes. We've got to find 2 routes to get from one place to another. I'm going to call the blue route this one. We can go from here to here by this route. I'm going to call the red route this one. Go from here to here directly. And so this and this will have the same enthalpy change. So that leaves our unknown value up here, and I'm going to call that, if we're using standard enthalpy changes of formation here, we should have standard enthalpy change of reaction left over. So if we put this into an equation, we should find that standard enthalpy change of reaction plus this value here. Again, I'm going to put these in brackets and worry about sorting out the pluses and minuses later, or just plugging it into the calculator. That is going to equal the red route this way minus 882. And again, what we're going to do here is we're going to subtract this term from both sides, and so we end up with just delta RH, standard conditions on this side, equals minus 882 minus, we've subtracted it, minus 594, and that gives me a value of minus 288 kilojoules per mole.